Hello, we are Group 7 in the Summer 2020 Senior Design 2 class. Our project that we are demoing is called easyherb. Our group members include Luna Vasquez, Lindsay Feldman, Chris Hernandez, and Kyle Patrick Magbu. Goals for easyherb include making sure that our system will only need minimum maintenance when it is turned on and that it is automated. Since the system will be kept indoors, ensuring that it is lightweight will let the user be able to move it around with ease. easyherb will have an easy-to-use interface that will let the user be able to see the system settings. Our last goal is to have our herbs grown in the best conditions while they're in the hydroponic system so that it maximizes their growth.
This slide displays the engineering specifications chart for our project. In this video, we will demonstrate the ones highlighted in the table. The first shows that the system measures gallons of water accurately to ensure the proper nutrients is distributed. The next is to show the reaction time of the lights when the light intensity changes. The last specification shows that the system can remotely update the state of the lights.
This is the full view of the completed enclosure for our hydroponic system. The enclosure is divided into three major parts. The first part we will discuss is the top section. The top section houses some of our major components. The top is able to open up to allow a view of what's inside it. It contains our PCB, LCD screen, speakers, and power supply. There was more than enough space in the end for all these parts. The PVC pipes connect to the bottom of the section to help support it and has wires going through them to connect all the subsystems together. The bottom part of the top section has the grow lights mounted on it. These grow lights are what will provide the herbs with light when the plants have not received enough in the day. The next section we will discuss is the middle section. The middle section is an open area with the 4 PVC pipes on each corner. It houses the 2 herbs, ambient temperature and humidity sensor, light intensity sensors, soil moisture sensor, and the top half of our watering system. The herbs are in 2 housing pots with holes to allow the water to return into the water reservoir tank. The final section we will talk about of the enclosure is the bottom section. The bottom section opens up in the back and houses our watering and nutrient systems. On the bottom we have the reservoir tank, which houses our water pump and the water temperature sensor. On the top we have the lower half of the growing medium for the herbs. On the left is the pH sensor that is hanging. The water pump tube goes from the reservoir tank up to the middle section where it drips water onto the herbs. The water will flow back into the clear tank where there's holes on the bottom for the water to return to the main reservoir tank. The top right corner has a nutrient system. The nutrient pump is mounted on the top and has one tube in the smaller clear tank that houses a nutrient solution. In the nutrient tank, it has a nutrient level sensor where it senses how much nutrient solution is left. The nutrient pump transports the nutrient solution from the nutrient tank to the main reservoir tank. On top of the water reservoir tank is a water level sensor that measures how much water is left in the tank.
This is the PCB for the hydroponic system and is the second iteration of the board. The red LED is on, which indicates that we have power. This right here is the DC connector. It is mounted on the underside of the board due to it being placed incorrectly in the schematic, but we were able to get it to function properly. Here you can see the power cable at the top and the LED showing that it is turned on. Here we have a reset button that will reset the MCU. These are all of our pin headers that we will use to control the system. The following headers are the ICSP headers that are used to program the microcontroller. This light is an indication light. This light is used to indicate that the code has been uploaded correctly onto the MCU. We will upload a simple blink LED sketch to show the PCB functions as expected. After the PCB has been tested, we will upload code to control the rest of the sensors from the board. This video is to show that the onboard voltage regulator is properly regulating the 12-volt input voltage that is used to power 2 of the pumps. Right now our multimeter is reading 0 and we are going to use it to show the 12-volt input, and then after we will show the 5-volt line to show that it has been regulated. So now we will go to any ground on the board and touch the multimeter, and as you can see it is about 12.6 volts. Now we will go to the other leg of the regulator and we have 5 volts coming out. I can also go to any 5-volt line on the board and show that it is 5 volts. In this video, we will show the bootloader burning. Once it is finished uploading, the green LED will blink. Now it is done uploading, so the green LED is blinking as shown. The next step is to pick our desired sketch, which is the blink LED sketch, and upload it using the Arduino Uno as the programmer. Now it should upload. Now the green LED is blinking 2 seconds apart, showing that the blink LED sketch is uploaded and functioning properly.
In our first engineering spec, we will display the lighting system. The light system should change within 5 seconds after an event is triggered. In the following video, we will show how the grow lights and light sensors work while connected to the PCB. The top part of the enclosure was removed from the body to allow the viewer to see a better angle for this engineering spec. A flashlight will be turned on the bottom towards the light sensors to show that when it senses enough light, it will turn off the grow lights. We will time the time it takes for the light to change once this event occurs. Here is our first attempt. As you can see, the lighting system had a reaction time of 1.6 seconds when the lights turned off because of the flashlight. This is our second attempt displaying the same trigger. The reaction time is 3.5 seconds. Now we will do the opposite, where the flashlight will be turned off and records the reaction time for the light to turn on. The time came out to be 1.15 seconds. We will do it one more time with the lights turning off because of the flashlight. The reaction time is 1.54 seconds. And now one last time of the flashlight turning off. The reaction time is 1.35 seconds. Since the 3 light sensors take an average, we will show 2 sensors covered and 1 sensor measuring light from the flashlight, proving that the grow light should still be on. Now we uncover the 2 light sensors and see that the grow lights turn off. Now we will cover 1 sensor and show that the lights stay off. The following screen recording shows our code taking in the light intensity from the 3 light sensors and computing an average, and then determining if the grow light should turn off or on based on the light intensity intervals we decided on. From our tests that we ran on our lighting system, the average time of the lighting system reacting to an event trigger is 2.59 seconds, which is well within our desired range for a specification of 5 seconds.
For our second engineering spec, we will be demoing the water level sensor that is a part of our watering system. The system should measure gallons of water in our reservoir tank with an accuracy of plus or minus 0.1 gallons. For the sake of demoing this engineering spec, our water reservoir tank is empty. Here we have 4 cups of water, which equates to 0.25 gallons. We add this water to our tank. This screen recording shows that the water level sensor measures 0.24 gallons of water. Now that the water reservoir tank has 0.25 gallons of water, we will add another 0.25 gallons of water. The water level sensor is now measuring 0.48 gallons of water with 0.5 gallons of water in the tank. The water reservoir has 0.5 gallons of water, and we will add another 0.25 gallons. The water level sensor is now measuring 0.72 gallons of water, while the tank has 0.75 gallons of water. We will now add the final 0.25 gallons of water into the tank, while there is 0.75 gallons of water inside. The water level sensor is now measuring 0.95 gallons of water, as the tank currently has a gallon of water. As we can see, for each of these tests, the error between the recorded amount of water and the actual amount of water added to the tank falls within our spec of 0.1 gallons of water.
For our third engineering specification, we will show how the user can remotely change the state of the light system via the app within 3 seconds. As you can see, the phone is currently connected to a Wi-Fi network. Opening the app, we are able to change the state of the lighting system. Timing the change of state, the first iteration took 1.72 seconds, and the second iteration took 0.87 seconds. The third iteration took 1.34 seconds, and the fourth took 0.9 seconds. Now we will disconnect from the local Wi-Fi network and use the phone's data. We can open the app and see that we can still control the lights remotely, and the response time is still within 3 seconds. From the table below, we can see that the longest test took 1.72 seconds, which is less than 3 seconds, proving that we satisfied the engineering specification.
Besides our engineering specs, we would like to showcase a complete operation of our hydroponic system. This will include the speakers, water system, and lighting system working simultaneously on the PCB.